the three codon pairs with the anticodon. Now, the first step was the first probing. At that step, when the codon-anticodon interaction is tested, GTP is hydrolyzed to GDP, and then this can basically dissociate. However, still in this position, there can still be the release of the tRNA if it doesn't match. So you have this through the hydrolysis form, this reorientation, what we call the closed form. Then it opens again, following the proofreading to test that it's matching. Now, what's really important is, and I'll probably mention this later again, is that what the ribosome checks is not really the matching of the codon and the anticodon, but it actually probes for the geometry of the complex. And that's also why wobble coding is actually possible. So it's not the sequence per se, but it's the way the codon and the anticodon interact with each other in three-dimensional space. And that's because you have this, this orientation where basically different bases from the ribosome, the mRNA and the tRNA all kind of need to form interactions in a organized way. And these can be identical between cognate and near cognate, so there can actually be mismatches, but as a general rule, and I think that makes sense, of course, most near cognate complexes are basically kicked out and rejected even before GTP hydrolysis happens. So this is actually happening at a very early step of the whole process. Now, once the GDP has been released, the tRNA is here, and now it basically needs to accommodate. So it really needs to basically go in to its final conformation, where it then is able to rotate such that the amino acid that's first facing away from the P site tRNA, it must be brought close to it, otherwise this could not react. And this is again a reaction step that can go pretty much both ways. It's a slow reaction, and again this gives another chance to remove the wrong or non-functional tRNAs because they would be slower if they are not near cognate. Now the tRNA has reoriented towards the P site tRNA, and now the transfer of the tRNA or the amino acid from the P site tRNA to the A site tRNA can happen, which will then lead to a translocation the A site tRNA to the P site. And that happens through a rotation of the small subunit. Now, there are two types of rotations or movements of the small subunit, and that's shown here from the bottom. So you can, on the one hand side, see that there's a rotation between the light blue and the dark blue, and then also there is a second movement which you can see if you look at the head of the small subunit, and that's a so-called swiveling. So in addition to the rotation, there's a perpendicular movement which is kind of swiveling. So again, a little rotation, but not between the two subunits, but now perpendicular to it. And both of these contribute to the probing of the codon-anticodon geometry. This is basically shown here as a cartoon. So you have the non-rotated, you have the ribosome in a non-rotated state, where here the A site tRNA is in the A site, the P site tRNA is in the P site. Once a transfer has happened, now the nascent peptide chain is attached to the A site tRNA, and in order for the A site tRNA to move into the P site, the ribosome or the small subunit rotates, And what happens under this in this situation is that the tRNA forms a so-called, or goes into a so-called hybrid state. So it's both in the A site and the P site, or it is in the P site and the E site. So it's basically at the bottom, so at the anticodon codon, it's still in the A site, but the business end, the CCA tail, is already moved on. So that leads then to this occupation of two different sites. And this now going back to the paper where I took the cartoon from before, showing you how dynamic the tRNA or the tRNAs actually act in this processing. And this is what I've told you pretty much at the very beginning of my last lecture, is that the tRNAs are actually extremely flexible. So if you put them in solution, they can really change within a very, very short time their structure, and the conformation does change while you're decoding. And you can see this here, where from the kind of coming in to taking over the amino acid from the P site tRNA, and then this one moving into the E site and this in the A site, you can really see that there are actually a lot of different conformations happening during this process. And each of these steps are kind of equilibrium reactions, and that allows the ribosome to really check that what happens is what you would expect. And since tRNAs are very flexible, but they are kind of optimized by their modifications that I talked about before, this really allows translation or the ribosome to check that everything is kind of properly done, and that really, this is a quality control step that shows that modifications and structurally this tRNA are not impaired. So this is basically the reaction happening between the P site and the A site tRNA. So you have basically an attack of the amino acid in the A site that attacks the ester of the P site chain, and thereby gets this transition stage reaction where it then kind of flips back, and then the double bond here forms again at the oxygen, leading to a release of the P site tRNA. And now the amino acid basically, the chain sits on the A site tRNA, and again, now it needs to move to the P site. In general, anticodon and codon, as I told you, form this kind of anti-parallel mini-helix. And in most cases, the interaction is really what we would expect, AUGC. However, the third position is very often a little special, because there you can find the so-called wobble interaction that are supposed to not fit, or not being Watson-Crick interactions. Now, and one specific or special thing to be considered about wobble pairs is that they are not necessarily equivalent. So what you can see here for these canonical AU pairs or the canonical GC pairs, you can basically invert them. So if you would basically move this position here and flip it,